I think we need, can you hear me?
Yes.
All right. I think we need to start. So today I just want to also to remind you on how you can access things. So we go to week 2, and that is going to take you to Thursday. So today we are going to talk about the fundamentals of wireless receivers. So we'll introduce the concept. And also what we are going to try to do is to set the rest of the material we need to cover for this class. The other thing that you have for today will be under quiz. That ends, as you can see, at 11:45 p.m. today. So the reason I did it like that is because some of you could not be here today because of valid reasons, and they did not want to miss it. And that was the only way, instead of making it available individually, which, you know, it's a pain on Canvas, is to make it available to all of you. There will be, in this quiz, you will see there will be 4 questions, but 3 of them are the ones that have questions and you need to select an answer. It's a multiple choice. The last one is for participation, and it's going to ask you, did you respond to other questions? You say yes, you get 30 points for participation. You say no, you don't get. I mean, I don't know who's going to say no. Obviously, there are people who will not. But this is an artifact of how Canvas does it. All right, so I had to do that this way to be able to get the points. All right, so 60 points for this is our first quiz. It's gonna is based on what you have for on 5G and 6G, what you've learned, you know, when you read it, like as I said, a magazine or something, when you read something, but you don't necessarily need to, so you know where, what I'm asking you is so fundamental that you should be able to find or to remember it. Okay. The other thing that we have for this week, and you go under assignments, is homework number 1. And homework number 1, it does have it is a homework that does 2 things. Gives you an opportunity to review transmission lines, the fundamentals, and then allows you also to do a download of ADS. I know that there were a number of students who maybe have taken 322 some time ago with a different instructor, and may have found that homework difficult, but I have to say this. I will give you enough information. I will ask you to go back and review 322. We cannot repeat 322 in this class. All right, so please keep that in mind. The fundamentals of transmission lines were 2 things. Ideal transmission lines, know what are the different parameters. Matching networks, the fundamentals with like stubs, series, parallel, short or open. And then Smith chart. These are the fundamentals. When we say transmission lines for this class is the next step, all right? It's beyond just the fundamentals. And we will have to use those fundamentals to be able to build on. So for those of you who do not remember very well, I have made some things available. I will make more things available if you need that, but we are not going to cover the fundamentals in this class because there is so much to cover that there is no way we can spend that. Okay, so what you can do is that ask help from your team members for that, to give you material. Look at your material from 322, and then look at what I will give you. And we'll revisit it as we solve higher level problems in transmission lines, but we are not going to be able to spend extra time on this. So that's what I wanted to say. Now, I also have some reminders, and those will be, first of all, it has to do with how we symbolically represent things. All right, so probably you have seen an ideal transmission line represented symbolically with two wires. All right, and then we say it's one port, the two ends of the transmission line, we call them ports. Port 1, AA prime, right, has two leads. Port 2, BB prime in this case. However, a lot of times, as we go to higher level of complexity in circuit design, you're not going to see two wires representing the transmission lines everywhere. You're going to see one wire, and then you're going to see like a box, at least in the intermediate. Later on, you're not going to even see the box. But in any case, for now, you're going to see a box like the rectangular here that says Z01. And that is another way of representing a transmission line in a simpler form. The same thing applies for stubs, all right? Also, another thing that I've said, at least myself, multiple times in 322, and you will hear it here. If you don't know what characteristic impedance to use, if you're going to go to the Smith chart, because we need to normalize, use as a reference impedance 50 ohms. If you don't know what to normalize with respect to, use 50 ohms. But you have to be careful to use it everywhere, not just in one place and then you turn it into something else, all right? If you use 50 ohms to normalize anything and you use it across the board, you will never go wrong. So if you don't think you see a characteristic impedance somewhere, use 50 ohms and say, my Z0 reference impedance, that's how we call it, is 50 ohms, always, all right? And also people ask me, what is Y in? Y in is an admittance, input admittance, is measured in Siemens, which is 1/ohm, and Z input is an input impedance. It is measured in ohms. Please, I am sure 100% you have seen those things. Please review them. All right, I can give you an answer, but that's not learning. Well, you don't learn when I just give you an answer to a problem. You learn when you find your answer yourself. I can give you steps in between, but the answer has to come out of you to be able to learn something. All right. Any other questions about those topics that I covered so far? Okay. Also today, I'm going to have office, I decided every Thursday, we are going to have a problem solving session. I'm going to select problems, say, for example, some problems similar to the homework, not the homework. All right, make sure it's not going to be the homework that I'm going to solve. There are going to be some problems similar to the homework, which I'm going to solve between 2:30 and 4. I'm going to record that all of the problem solving sessions will be recorded and will become available to all of you, because I know the time I selected on my own, you had nothing to do with that. And I appreciate the fact that many of you are not going to be able to make it because you have a full schedule. All right, so those will be recorded. The lectures, I record them. However, I know that some people who will be absentee for the lectures, for good reasons, they would like to have an access to that. Please, it takes me 1 day to take care of this, because whatever the recording is, I have to remove people, comments, and anything that makes you visible. And so I have to go through some editing. To do the editing and upload it to YouTube, where I do, and make it available. It's not going to be public on YouTube, so I will have to send you the link. Then it takes me some time and I cannot do it immediately. So I will always have them available the next day. So don't ask me before the class. Tell me why you're not coming before the class. I would appreciate that. But remind me after the class or the day after that you needed that, because I have to tell you, I get so many emails every day that if I don't do something and then they pile up, I may forget. and I will have them to find you, your email to be able to. And that is going to take me more time and it's difficult. Okay. And being clear? It's okay. Okay. So today, let me now, okay, I'll tell you where I'm going back. I'm going here. So you will see one of the papers. I like to do that because I want you not to, you will see in this class, we don't have a textbook. Textbooks in this class are so expensive that I find it ridiculous. All right, so what did I do? I'm looking at materials like magazine technical. I mean, usually I get that out of Microwaves, which is a professional magazine for our area. And when I like something, I see the language, this is a short tutorial, which I found is excellent. But I had some modifications that I made on my own to be able to introduce the subject to you in a better way. But it's a great tutorial because it gives you a high level discussion about the receivers and what the issues may be and so forth. Also, it will help us introduce the topic. So that is a primary reading for today, for this lecture. And we will come back to it as we will cover the different components, and I will talk about this next. So I have that. The other thing that I had is one more publication that I put there for your information, but this one is the primary one that we will cover today. So first of all, I will show you this here, and at some point I will start writing. So you're gonna see this becoming half of the page, and then I'm gonna write next to it. But now I want to introduce to you a schematic of a present day receiver. So if you were to have if you have an old phone that you have not returned for a new version, you can open it up. In fact, I have one at home, which I forgot to return. So you can open it up, and then you can see where your RF components are. They're not going to look like this, obviously. They're going to be like little chips connected. But if you were to look into this carefully and identify what a receiver does, a receiver receives an RF signal, and then they try to get information out of it. So I have a question for you, which I believe you may be able to answer without me making a statement, all right? So the question is, if I need to speak with, your name, remind me.
Cody.
Cody, yeah, thank you. If I need to speak with Cody, and Cody is not in this room, but is somehow in a different building, I will have to call him, all right? Why do I use RF frequencies to do that? Could I just use a DC field? Why do I have to go to RF? I mean, DC fields exist, all right? An electric field at DC out of charges, that's what it means, a fixed charge. If I place here a positive charge, it's going to create an electric field, not electromagnetic. Yes?
If you just have DC, you have, in a purely DC environment, you have no change. There's no opportunity for any transmission of data. There's no possibility of any signaling or movement.
Yes, that is true. This is a derivative reason, all right? So second level. But why people wanted to go primarily to RF and not DC? Yes. Frequencies RF, obviously. But because, RF fields, electromagnetic fields, travel a lot faster, travel a lot further, all right? And easily can go through a lot of different structures and a lot of different materials. The same is not true with the DC field. I mean, unless you have a huge charge, all right, sitting somewhere, and you can be able. DC fields, however, are utilized for near field approaches, right? Because you can still see things, maybe not as extensive information to send it, but RF is primarily because of the distance, the need to go a distance. So that is. Now, in addition to that, of course, when I call somebody, I want to speak, all right, with this person. Our speech, our voice that comes out is at a frequency, but it's not a very high frequency. It's very low, it's audio, okay? And therefore, I want to take this information, whatever, it could be text only, it's not mine. And I have to translate that into bits, all right? And then use this information to do what? Modulate the RF signal I'm going to use then to radiate. So we call that RF signal the carrier, all right? So in the receiver, the carrier is the signal that helps us connect long distances. It is received by the antenna, and the carrier carries information. I don't care about the carrier. I don't want you do anything with that. The only thing, by the time it has come to the antenna, it has done the work, all right? The only then thing the receiver does is to receive this frequency signal, which is modulated. It could be modulated in different ways. Have you heard about modulation of signals? How many different ways you have for modulation? Okay, a number of them, all right? And on the basis of the modulation, you have different types of receivers. So you take the signal here, which is high frequency, and then you need to process it to get the information here. So the receiver is from here, the moment it comes to the antenna, to here. That is the most updated in terms of technology receiver. Now, as you can see, there are different, this is a system, right? There are different components that make it part. And then, so here, these are my notes that I have added to the paper, and then I put my name underneath it so you can see what I'm adding, all right, when you read something. So, first of all, you see this wiggly shape with lines. That's a very interesting thing. This wiggly thing, let me write also, if you can allow me, just to make sure I can do this. Okay. On left. Okay. And on the right, oh, you need something else. Let me see. Oops, no. On the right, I need to start. Get notes. My notes. Let me write that so I can save it. Then go there. Okay, so we'll do this again. There, and for the right, oh, wait a second. Modify. Okay. Let me see. I think I can write here. Can I write here? No. I can do this. Oh, there. Okay, good. So I'm gonna be writing here. And then from here, we're gonna look at this. You see both of them, is that right? Okay, there is a little bit of delay. So when you see, we are talking about filters, and here in the particular case, there is a one specific filter, which is called the surface acoustic wave. So these are very interesting filters. We are not going to study those filters today. In this class, we are going to study other filters, but you have a choice of filters that come from different materials, different designs, all right? We're not going to cover all the filters. We're going to cover the ones that you can easily do on ADS. But when you see something like that, when you say, I have a filter here, usually the way we show it is like this. Okay. You see something interesting here? That in this filter, there is something here and something there. What does that mean? That this is a band pass filter. Because one of these, the first one shows low frequency. The middle one shows the band. The upper one shows upper frequency. So when I erase this and that, that means there is only a band that I leave behind, if you see it. So you understand, if you see in any technical magazines or publications, this is a filter and it's a band pass. All right? Okay, the next one, what does this filter do? Our signal is around a frequency, all right, and has a bandwidth. So you're going to have a signal in the frequency domain. In the time domain, the signal is going to look like this. Whatever, all right? But in the frequency domain, in fact, I'll make this easier, right? In the frequency domain, the signal is going to be centered around the frequency of the carrier. So if your carrier is 5 gigahertz, for example, and that we call it F sub C, then the signal you're going to receive is going to be something like this in the frequency domain. Okay? So why do, if my signal comes like that, why do I want to use a filter that will allow what the filter does is, for example, if this is your signal and you have a bandpass filter, the bandpass filter in frequency looks like this. So this is your center frequency will do this. This is the lower frequency. This is the higher frequency. All right. What this therefore allows, if we, after the antenna, have a bandpass filter like this, it will only allow this part of the filter to go through. All right. It will allow only this part of the carrier to go through, meaning that all of this noise here is going to be eliminated. However, there are other times when next to you, there is another phone or there is another device that transmits in a slightly different way or uses a different channel. And we call those blockers, at least in this. So meaning, if my signal is this, but then a different signal comes next to it and it's like this, all right? Then what I may want to do is I have to remove that, but I have to let mine go through, which means I will have to redesign my filter here to be more restrictive in terms of what frequencies allows it to go through, and then make it like that. All right, so practically, this is going to allow my signal to go through this one, and a little bit of the other signal, which eventually we'll have to eliminate also. All right, and a little bit of that. So practically, the filters are good for two reasons. They remove all of the noise that is out of your main band because you don't want to have to deal with this. The receiver is a non-linear device. What does the non-linear mean? It means that if you take a signal at a given frequency and you pass it through you will have byproducts of other frequencies. That's what nonlinearity creates. And you don't want to therefore having the noise outside to create byproducts that come into my band. All right, so I'm gonna leave that. So the filter does two things: eliminates that, this noise of your signal, and then also blocks other signals, other frequencies which are unwanted. So that is very important filter, the first one. Then after the filter, what do? We go to the next one, which is a low noise amplifier. And we're gonna cover that in this class. Why do we need a low noise amplifier? Because the signal that comes, what kind of a level do you think in terms of watts? How small of a signal we're gonna receive?
Microwatts.
Microwatts, if not smaller, depending on how far you are from a repeater, for example, right? So from a node. So this is very small. And therefore, to be able to do all of this processing later, I need to have a higher strength in my signal. So we pass it through an amplifier. Why do we call it a low noise amplifier? Because the signal already has noise that comes. We have been able to remove the noise outside of the band, but there is noise inside the band. So if this one, well, it's a filter, it has to be a very good filter with low noise. But if this adds additional noise, then the signal that is going to come here is going to have more noise than it had when it arrived at the antenna. So we need a low noise amplifier. We're going to learn how to do that. Then it goes here. What do we do here? We split the signal. Sometimes this is called a splitter, all right? And it's part of the local oscillator. So the local oscillator is one. The local oscillator creates one frequency. And the local oscillator for this creates a frequency that is very close to the FC, the frequency of the carrier. Very, very close. All right? So it creates, how close it is, it depends on how low in frequency we want to go after the mixers. So what this LO does, it goes here and do a splitter, which here creates a version of the incoming signal, but with 90 degrees out of phase. So if the incoming signal is cosine omega t, for example, is simple, what comes out of here is a sine omega t, but has all of the information of the initial signal. All right, because all the information is just 90 degrees out of phase. You introduce it. And then in the mixer, we mix the local oscillator frequency with this. And we create a signal that we call the Q signal because it's quadrature from the original. All right. And the original signal, half of this signal goes to this mixer, it is in phase with that, that's why we have the I in phase, and is mixed with the same local oscillator frequency. And then as a byproduct from the mixing, what does it do? The mixing creates a very low frequency, which is the difference between the local oscillator frequency and the carrier frequency, and higher frequencies, many others, multiple others. Now, we want to keep the low frequency. All of these frequencies have the same information like the original signal, all right? So we don't need to have all of these frequencies to find the original information that we have used to modulate the signal. So we want to keep only the low frequency, all right? The low frequency from here, which is the difference between these two, the frequencies, and the low frequency from here. So we pass them through two low pass filters. That's how you show a low pass filter. Or, as we talked about the filters, if you show them like this, low pass is also that. You eliminate band pass and high pass, you have the low pass. Sometimes you will see it both ways, all right? I just wanted to show you. Or you will see it like that, is much easier to understand. So now you got a very low frequency. Low frequency meaning if your carrier is at 10 gigahertz, 10 times 10 to the 9 hertz. Then here, this one can be 40 megahertz. 40 times 10 to the 6. All right, could be 10 megahertz. Very low to the point, a very frequency to the point that I can take that through an analog to digital converter and make the analog signal into bits. And then where do I go from there? I'm going to a microprocessor where we process the signal and we get the original information. Could be voice, could be text, could be. And that's how this a receiver, like all of the phones, work like that. Okay. Now, this is an architecture. That's how we call this, the architecture of a receiver. All right. And in this one, what have you seen is that every part of this has simple lines. In architectures, that's why I show you how a transmission line, it's sometimes I said has the rectangular box with a characteristic impedance. Most of the times it does not. But how are you thinking about that, all right? Where do you think I will have these simple connections will be transmission lines, and where will these be single wire? Do you remember why we use transmission lines? To?
The transmission lines will be on the on.
Yes. Before we go there, we use transmission lines for high frequencies. We don't use transmission lines for DC. All right. For those of you who have done computer circuits, all right, you don't need a DC. You don't need a transmission line to send a DC current. You need a simple wire. Hopefully done well, so you don't have very much ohmic loss. All right. However, when you have an RF signal, you cannot send RF on one wire. Why is that? Yes. That is true. That's part of the transmission line design. But there is one thing that makes transmission lines, meaning two lines, all right? Transmission lines are two lines. You may see only one, but the other can be a ground, all right? The transmission line can be my ground if it's conducting. And that can be only one wire. You will see microstrips like that. What happens with RF? In RF, if you remember, the signal changes over time. All right, positive and negative. If the current is positive and you have that direction, that means it goes like that. If you keep the direction like this and the current becomes negative, it means that it goes like this. But the current cannot go and stop somewhere. What do we know about current? It has to go on a closed loop. All right, the current cannot just be like a charge sitting in isolation. The current is nothing else but electrons that move constantly. You may have a source to supply them, but if you don't have a source and you have a current, it goes on closed loops like the magnetic field. The current goes on closed loops. So in the RF, you need to have a closed loop to be able to have your current through. All right. In DC, you don't have currents that flowing, rather you have charges. And charges can stop and go, all right? They can stop in one location. You can put a charge in one location, practically. Now, if you move positive charge from one location to another, yes, you have, you create a negative charge somewhere, and all of this becomes, an issue of how you do that. However, you don't have that continuous flow that you have with high frequency currents. All right, so you need to remember that. And that's why the transmission lines are important. So to what your colleague Daniel said, everything in high frequency, it has to be a transmission line. Everything above DC, rather, is going to be a transmission line. So from this point up, before, from the antenna all the way to the ADC, you have a transmission line. And then from ABC on, you have digital lines, okay, as we call them. So that's how this is going to be. What are we going to do in this class? Any questions? Yes. Yes. When you try to come and process these two signals, then the 90-degree phase difference gives you a much better extraction of the information as opposed to what you would have without it. Processing. Yes, yeah, exactly. So it's like it minimizes the errors in the processing. All right, and then it's coming much faster, much better in terms of error extraction or reduction. Okay, so now we are going to do filters. Filter design, the way we are going to do it is going to apply both to this, which is a band pass, and to the low pass filters. All right, and you're going to be asked to design them in the process of doing that. We are going to do the low noise amplifier. We're going to do the oscillator and the mixers. Now the splitter here is a simple thing. You're going to do it. You don't have to, I mean, other than looking at the design and a schematic of a splitter, how to do it. There is nothing really more to that. Now, before we get there and try to do filters, low noise amplifiers, and whatever, so we can claim then that we would be able to put this together, we will need to do two things. We need to talk about transmission lines, including their physical implementation. All right, because when we speak, as I said, we'll go one step higher in transmission lines. So far, we have dealt with ideal transmission lines. And ideal transmission lines, here, we would show them like that, all right, in our problems. So the question is, okay, I have this transmission line. How am I going to make a transmission line for a 10 gigahertz receiver, for a 5 gigahertz receiver, for a receiver that I have on my iPhone? How am I going to make a line that is going to connect my antenna to the filter, from the filter to LNA, from the LNA, and so forth? Well, there are different types of implementation technologies, and we are going to talk about this when we go to transmission lines, all right? So we are going to talk about the different issues, which is going to be, in fact, the next topic we're going to have. And then we are going to talk how to, therefore, like a microstrip or coplanar waveguide. A microstrip, for example, is something like that. You have a ground, you have a wafer, for example, like this. You have a ground underneath it, and then you have a microstrip on top. And this is the three-dimensional view. All right, so this is conductor. Let me see this one. So this is conductor. This is conductor underneath everywhere. And in between, you have a dielectric to separate them. Now, these are two lines. Why is that? One, the current, if I excite this line, the current on this line is going to go. I'm just doing some summary right now. All right, I'm not doing it carefully, just so then we will revisit it again. But the current in a conductor like that, if I were to plot it, it goes like this. What happens if a current, let me see. I'm not very good with my drawing today. Yeah, horrible. So if I were to redo this again, up here, if I were to take a view of the current, a cross, a path, then I will see that the current will have its maximum at the edges. Why is that from electromagnetics? because the charges in, or when it's a current, are electrons, all right? Because the charges like to go where? Well, there is surface here and there. If they would like to go only on the surface, it would be most of them at the center. They like to go to points. Remember, edges. They love the edges. So the edges are here. So it always, you remember from those of you who did, we did 322 and we talked a little bit about the charge distribution in statics. If you have a conductor with like a square, all right, then it's all, you put a charge on this square conductor on the surface of the conductor is hollow inside, for example. Yeah, inside they're not gonna go on the surface of the conductor, but on the surface they will prefer the edges where there are sharp points. That's where the charges are. And that's why when you want to, like when you have bad weather and you want to make sure that you don't have a lightning going through yourself, usually they put very sharp metallic edges, very high up, all right? So that's what attracts all of the charges. The charges do not like to go on a flat, nice surface. They like to go to edges here, here, and anywhere that you see an edge. So the edges here are 4. 1, 2, 3, 4. And that's where the charge is going to go. Okay, that's number 1. If the charges concentrate here like that, how are they going to look down below? Are they going to be out here? Or they're going to be closer to where? Because you have a positive charge here. So let's assume that you have, or negative charge, whatever. Let's take statics for a moment, all right? Let's take statics. If we had that with a static charge, and let's assume that the microstrip had positive charges, then you would see all of the, I do them here. All right, so you will have positive charges here and on the side, obviously. Okay, like this. What would these positive charges do? Attract negative charges here below. So where would the negative charges look? They're not going to go out there. They're going to go as close to these ones as possible. So where would the negative charges go? Here. All right, and fewer outside. There will be a few outliers. So practically, most of the field between your ground and your metal concentrates here, which means that on the ground, your charges, more or less, they're not going to be as sharp as here because the ground, you see, it does not have edges. I mean, this is very far away, as opposed to microstrip. The ground is flat and everything. So the charges on the ground will distribute like that. Oops, not. Something like this. But they are going to be, and maybe a little more sharp here, all right? Maybe a little more sharp, but they are going to be somewhere underneath it, which means that if my current on top goes like this, I'm going to have a return current on the bottom that is going to look like this. And then granted, it's going to be a little further out distributed, but there I can see the return current in the ground. So practically one infinite ground with a strip on top, it makes a 2-wire line. Okay, that's the microstrip. We use it extensively. But people moved away from this, as you will see, to some other structures. Why? Because I don't like these things that extend. Because what if I wanted to put another microstrip close to it? Then the current of the other microstrip underneath here, and this one they will mix up, and I will have what I call crosstalk. All right, so these are the kinds of things we'll see which are important in design. And then, of course, all of these geometries, you can say, why then did we do this? But in reality, it's so much more complicated, because eventually this helps you make good designs. This helps you understand how different reality is from the ideal. But the ideal helps you start a design, say design dot 0.0, and then all of these facts, which for high frequencies become important, we call them high frequency effects, how the current flows like that, how it goes here like this, and so forth. Those then can help you take an ideal design and improve it. So it becomes 0.1, that one, design that one, and then even more improvement, design that two. That's how design happens, all right? And then you will, ADS will help you with that. It's going to help you get a sense of how things work. So we're going to do transmission lines. After transmission lines, all right, so we'll do transmission lines. After transmission lines, before even we go to filters, what are we going to do? We are going to introduce network theory. Why is that? Because of the following. Let's assume I design a filter, all right, with a filter from microstrip. I'll do a design for you here. Schematic is not a good design. I'll just show you a schematic of a bandpass filter. It's going to be microstrip, all right? So I'm only showing the top. It's going to be like this. An incoming transmission microstrip line is going to have a small cut of a small piece of a transmission line, another small piece, all connected like in near proximity, another small piece here, and then finally a line like this. All right. Another type of a filter can be something like that. An incoming line, which we call the feed, the input port, if you like. So here the filter starts at this point. That's AA prime port and ends at this point, BB prime. Or it could be something like this. And that can be a low pass filter. Okay. There is always an input port and an output port, which means the following. In an ideal form, I would say I would have, if I go to ideal representation, let's assume that all of these designs here with the metal, I put them in a box and I say, well, this is my filter, which is not a good box. Do this. Well, okay, that's what you get from me today for a box. And then this is your filter, whatever design it has. And then you're going to have an input transmission line, which we are going to show like this. And an output transmission line, which we are going to show like that. So that's input, output, A prime, B prime. Okay. What happens when a wave comes here? We said this is a bandpass filter. How does it look in the frequency domain? A bandpass filter, if I were to do it in the frequency domain, and that's frequency, it will be something like this. Oh, well, now I don't need that. it will be something like this. A simple one. All right. So what does that say? This is what goes through. It says at one particular frequency F, center frequency, and this is F, excuse me, this is F, and this is the signal that goes out. So let's call that B, all right, B of B prime. And that's versus frequency. So if there is a signal, if there are signals, different frequencies that come through AA prime, only the frequencies at BB prime, I'm going to have a voltage applied only for this range of frequencies. And what the voltage that I'm going to have here, of course, this is only the magnitude, all right? There is going to be phase, my guess is, but I'm showing only the magnitude for this voltage, just to simplify things. What is going to come here is going to go from 0, from DC. It's going to go up to maximum, and then it's going to come up, or very high frequency will be 0. So practically, for a filter, this port, if I come here, is almost like a open, all right, below, and or a, depending of course on what I'm gonna see as phase, can be open or short, all right, but in any case, it will be the voltage, let's say short, assuming 0 voltage here, short here, and another short there. So practically short here and a voltage at this point. So, and then what happens if there is nothing that goes through? All of your power that comes here is reflected, all right? So in these two regions, all of your power is reflected back. It does not go through the filter, and only here it goes through. But what happens even when it goes through, there is part of the power that is gonna go back. So if I have a an electromagnetic wave signal that comes like this, it at every point, for any frequency here, part of this is gonna be reflected, and part of this is gonna be transmitted. All right, if my source is at this point. So I need to characterize both the reflection and the transmission. Why is transmission important? I mean, you could say, if I know the reflection, then I know the transmission. Well, only in a magnitude, because the power, if you assume that there is no loss here, only your power is conserved, all right? But for a voltage that has both magnitude and phase, the transmission coefficient is important to show you what is the phase of the signal here. Okay, so you have to characterize this and this. And then what if your source comes this way? Yes, you're going to have a filter the way we do them. They're not active filters. These are passive filters. They're linear devices. So practically, and then most of them will be symmetric. So you will see the same thing. But in reality, if you have 2 ports, and for each port you have 2 coefficients to characterize, then you need 4 coefficients to characterize a 2-port network. So we call that a network, and then the coefficients we will need to characterize it, we call them scattering parameters. So we'll go to network theory to be able to talk about this, right, carefully. With that in mind, then we're gonna revisit matching networks, okay? Why matching networks are important? Because you cannot do a low noise amplifier without matching its input and output ports. So the fundamentals are transmission lines, network theory, and matching circuits. And matching we'll do with the Smith chart, because it's very difficult to do it otherwise. And then after that, we'll do filters, we'll do low noise amplifiers, and then everything else is just a combination of all of these things. All right, so that's how the class is gonna go. Okay, here, I wanted you to become familiar with, let me, in fact, remove that. Now, I want you to become familiar with these, the definitions, because, we are going to use these names without necessarily redefining them. All right, so you have to just understand the importance of these components, now we call them, on the receiver. So the receiver is a system, and each of the things I talked about, the transmission lines, which are important for the connections between the components, all right? An LNA is one component, even if inside it will be multiple components. A filter is a component, all right? A mixer is a component. A local oscillator is a component. And all of them together will make a system, all right? So we are going to keep the system in mind as we do the various components so you can remember why they're used. So if you go down to this one, they will explain very carefully, and we're not going to do this now. I don't want you to read all of this for the class, but as we do the mixers, we'll come and remember that, all right, when we come to mixing. Or, for example, here it becomes a little more complex when you start looking at every time you introduce a new topic. It becomes a little more complex on how this information helps in the system, all right? So what we're gonna do in this class, we're gonna keep this next to everything else we have. So make sure you remember that article, because we're gonna do it every time to explain why adding one more component is important and what that does to the initial signal that came to the system. Then there is another thing we are going to talk in this class, and it's noise. Noise is everywhere in a electronic system and in a component, and there is noise that comes from different parts of the system. Noise can come, ohmic loss practically becomes noise, all right? So anything you lose into into interconnects, anything you lose into any conductors you are using, that becomes ohmic loss and becomes ohmic noise. Then you have noise from active devices, all right? And then you have noise from high frequency effects. Now, each component will have its own noise and will characterize it. But then when you put components one next to the other, your system then has a total noise, which is the result of all of these individual noises. And there is theory, we'll talk about that, okay, that we will use when we know the individual noise of every component, how to find the total noise of the system. There is, for every component, a very important parameter, which we call the signal to noise ratio. The signal to noise ratio is important to keep it under control, because the moment your noise increases and your signal to noise ratio goes down, it becomes a problem for your receiver. All right, so I wanted to introduce these concepts because we're going to come back and look at this. Okay, so at this point, for the beginning of the class, what I would like you to do is to become familiar with this, all right? And also, just without going into specifics, just read up to the structure of the receiver and nothing else, all right? So read section 1. So section 1 is practically what I would like you to read as from this. On Tuesday, we are going to start talking about, let me take you then back to, okay. Let's go back now. to our modules. You remember where you see the course schedule? I will follow the course schedule very carefully. So Tuesday, we start with transmission lines. I will introduce microstrip and complainer. I call it review because in the mix of these, the macrostrip and complainer waveguides are two geometries that practically are used to develop transmission lines. But blended with that will be also some theories that we have seen before. And if you want to be able to solve homework number one and also be prepared for this, at least in terms of knowing the fundamentals, I would then like you to go back to your homework and read this one and go down here. These are things that we covered in 322. What is a quarter wave transformer? All right, how we use it. What is a series stub? How do we use the Smith chart for that? All right, series stub. How do we use a short and open, a shunt stub, and so forth? All right. I'm gonna do them, but as we do things, but I will go fast. I'm not gonna slow down because this is material. So as you work in your homework, read these very carefully. All right. Remember what? Look at your notes, personal notes that you have from 322 that may feel more familiar with, and then try to look at those and help yourself with the homework. But also, it's not only important, and that's why I gave you the homework, that you remember this is when we go to transmission lines, these things will be critical for Tuesday. And any questions so far? Yes. I have a lot of Smith charts. I will post one on Canvas today. I have a lot of electronic. Yeah. In fact, there are a lot of Smith charts. I'll tell you how I found mine, all right? I went to Google and you said Smith chart. And you try to stay away from the ones that have everything in there. All right, find the ones, but I will put one also myself. This is how you do it anymore. When you go, another thing, in everything we'll do in this class is going to be open source, open everything. You can bring your laptops, you can bring anything. The one thing that I will, in tests, for example, I'm talking about, or in homework, all right, you can use things from the web. However, I will consider you responsible for writing down the right thing. Don't just go there and write down something. There was a time many years back, and I think I can share that experience with you. I asked a class what was a resonance. All right, resonance is an electronic resonance in circuits. I mean, it was a 322. What is a resonance? Probably you have seen those from circuits classes. What happens when you have an LC circuit? What does it do? Resonates. All right, what does it mean that it resonates? There is a particular frequency for which all of the electric energy from the capacitor translates into magnetic energy in the inductor, and then the other way around. So if you stick with that frequency, that LC, if it's like an LC in parallel, an LC connected like this, it's like independent. It operates. It's like it goes into a resonant mode, as they say. I mean, It goes on its own. There is no need for anything. It never gives anything out. All right. I mean, you can excite it for a moment and then it keeps like going through this resonance forever if there are no losses. Okay, that's electronic resonance when at frequency where your capacity of electric energy from the capacitor, it transforms to magnetic and the other way around. Okay, I asked a question. I asked not equations, just, and people wrote down mechanical resonances. They went to Google, they got what a mechanical resonance was, like a pendulum, whatever, and they put it there. And I was thinking, no, that is not the way to use the web. We have tools, all right? We have many tools. These are the good news. The bad news is that a lot of these tools, a lot of the information there is incorrect. I cannot tell you how many people have published solutions to problems which are total garbage. But there is no editorial board, all right, to be able to correct things, especially if it's like one-off kind of a publication, all right? So when you go out to look for things, be careful on what you are looking for. It's more difficult to select the correct answer out of a sea of wrong answers than it is to create it yourself. But I will give you that opportunity to go and look, because a lot of times we learn, all right? I mean, the web, if you can be very critical in what you select, can be very informative. Now, for example, I have access to papers myself that before the internet and all of this, I would have got the library and found them. I did not know that they would ever exist. So we have access to a lot of material, but it has to be the right one. Okay, so you're going to have this open for all of the homework, for all of the tests, and the final. But don't believe that that replaces your study or your learning. All right, the worst thing to do to somebody is to give them infinite amount of information if they don't know exactly what they're looking for. Yeah. In any case, that is, I think we'll start on Monday, and today we are going to have a problem solving session, okay, which I will record. Thank you.
But the homework, if I have a quarter wave here,
Yes.
but this node is complex, can I use this formula? No.
Not
No.
for real, but
It's only for real.
it's only for real, this formula.
So
But if it's quarter, and you can find, for example, how it's going to look here at that point.
so
Yes.
I use this big
Yes.
formula.
Yes.
But since it's a quarter, so this goes to infinity.
Okay. Well,
So
if
what do I do?
no, before, because it goes to infinity on both sides, so you keep only the large terms. So if this goes to infinity, that practically is very small compared to that. If this goes to infinity, this is very small. So you have two terms and then that cancel out.
This cancel out
Yes.
the tangent.
Yes, because this is so much bigger
Mhm.
than this one. And this is so much bigger than this one that you can ignore this. And then eventually that becomes, all right?
So
And so, I mean, look, if you put this to zero, what is happening?
but if this goes to infinity, what do I do? And this goes away.
Yes.
So I only have this left.
You are gonna have J Z naught tangent beta D over J RL plus J XL tangent beta D. And that
Goes away.
and then that's what you got.
Okay.
Okay.
Thank you.
Sure.
My name's Garrett. I didn't take 322 with you, so I'm having
Yes.
trouble getting started.
Oh,
So
okay.
from what I can tell, this is supposed to be a stub tuner?
Yes.
Okay. And so you're supposed to use that to modify this.
Yes.
you
So
can
you're
get rid of
supposed
the
to find
reactance.
D. Right.
You're trying to get rid of this
Yes,
reactance.
yes. Because when you transfer
And then
that
you can-
through a quarter of a wavelength, you can choose this one. if you wanna choose this, I mean, how much did I say? 500 now. You can choose it if you want, but before you choose it, I would suggest come here
Mhm.
and then look at the input impedance at this point from here.
Okay, so. But with the way this is set up, how can I adjust this so that it actually,
D.
but it, since it's on the other side of the quarter wave transformer from the load, how does that actually modify the load
Yes,
reactance?
yes.
Really?
First of all, the load is gonna be modified by two things.
Right, the quarter wave's distance from it.
And then the value which you have not
Right.
specified yet.
Okay,
All right, so you'll come here. And then you have an additional parameter to
Mhm.
calculate. So here you're gonna have to calculate Z01. So the real part here
right,
is this.
okay,
And then you have to find D. So the imaginary part of this here is canceled by that.
okay. Okay, I'm just,
So do it
Because-
step at a time.
right,
Yeah.
because every time I've used a quarter wave transformer with an imaginary, or with
Yes,
a complex impedance, you've had to use a Smith chart, and so. and
Well,
all the
yes,
examples-
or use the formula.
Okay, all the examples that you also showed were
Is
you
a
used
real
a
then.
quarter wave transformer with,
Yeah, but it was real. But
Right,
in this
right.
case, you're just gonna use the formula.
okay,
No. Well, no, in this case, you have to use the formula,
which formula?
which is like when you have a section, you have a section of a line
Mhm.
and you wanna find the input impedance.
Right, so just this one?
No,
Oh,
no,
no, that's
no,
for
this
real.
is for the, yeah, no,
Yeah.
here you have a imaginary. So there is a
Right.
formula that gives you the input impedance for any given length of line, for any
Mhm.
load,
Okay,
which is
with the quarter wave transformer there.
with any length.
Okay.
There is a formula that has
Mhm.
tangent of something. You remember this
Oh,
formulas?
tangent beta L
Yes,
and
yes.
everything.
Use that one.
Okay, okay,
Yes.
okay. I'm
Yeah.
done. All right, and
But,
you're gonna
yeah.
kind of go over this a little bit in
Yes,
office hours,
yes.
right?
I'll do a different example.
Excellent.
Yeah.
Excellent. Thank you.
Hello?
I got a question.
Yes.
So the ADS license, I had already applied for it before you sent out the homework. So
Oh,
I don't
okay.
have the application. Can I send you
Oh,
my?
that's okay. Yes, yes.
Okay, I'm having issues still with it because my host ID changed.
Uh,
And then when I sent to get it, they sent me the wrong host ID.
Well, that's why we did it so early. So we
Yes.
give enough time to everybody before we start with any IDS to have it
And I'm
available.
sending out another email
Yeah.
tomorrow if I don't get a response
Okay.
because I'm still waiting.
Or you have to go there in person. You see that the IT in our department, you can go there by yourself and ask them.
Well, I know what my issue is on this.
Oh, okay.
The host
okay.
ID was, it changed
So
on
you
me
know that.
between
okay.
my license and then they used the wrong host ID. The company did when it was my last license.
I got it. Okay.
And they haven't responded since that email.
So the company has done that.
Yes.
Oh. Okay. Well, we're
Trying.
Yes, that's good. Thank you. And also we may use they may give us a lab, an open access lab.
Okay.
To be able to do that there.
I figured
For
if
the
I could
time
have it
being.
on my laptop, that would
Yes,
be a
then
lot
yes,
nicer.
yes.
Okay, thank you.
Sure, sure. I,
I sent you an email about the common disability accommodation.
yes, yes,
So, yeah,
yes,
the-
that's good.
okay.
Yeah, yeah,
So, yeah, if you could ever get a chance, just,
absolutely. Oh, yeah, to sign it.
Yeah, yeah, that's
When do
good.
you, yes, I have to do that.
yeah, sorry.
You're right,
That's-
you're
that's
right.
the thing,
For
yeah.
that, yes, I will have to sign it.
Mm,
Yeah,
yeah.
thank you for reminding me there are other people that I need to do.
Okay, yeah, thank you.
Okay, thank you. I don't know.
I'm listening to the presentation you talked about last time,
Yes,
for my pieces.
Yes.
Do you want to go over sometime like on Tuesday next week?
yes, yes.
Okay.
Tuesday is good. I'll be here, yeah, Monday, Tuesday, anytime after Tuesday, I'll be here.
Okay, well, like 4 o'clock, hopefully.
4 o'clock is perfect.
Okay, awesome. See you then.
Okay, take care. Hello.
How are you doing?
Good, good. Let me just turn this off for a moment.